Somewhere out there, in the deepest reaches of space, there are monsters lurking, cosmic behemoths so powerful they outshine entire galaxies. These aren't just stars or planets. They're quasars and active galactic nuclei, the universe's most violent and enigmatic phenomena. Imagine an object so bright, its light travels billions of years just to reach us, carrying secrets from a time when the cosmos was young. And at the heart of each one, a supermassive black hole, a cosmic engine devouring everything in its path, unleashing energies beyond comprehension. But here's the thing, these celestial titans aren't just destructive. They're also some of the strangest, most bewildering objects in existence, defying the laws of physics as we know them. Today, we're venturing into the unknown, exploring 25 of the most bizarre and mind-bending discoveries about quasars and active galactic nuclei. From jets of matter screaming across space at nearly the speed of light, to mysterious flickers that shouldn't even be possible, these cosmic anomalies challenge everything we think we know about the universe. Picture this: a single quasar can produce more energy in 1 second than our sun will in its entire lifetime. How, why, and what happens when these cosmic powerhouses collide, warp spacetime, or even vanish without a trace? The answers will leave you questioning reality itself. This isn't just a journey through space, it's a voyage into the extremes of existence. We'll uncover how quasars act as cosmic lighthouses, illuminating the darkest corners of the early universe, and how they might hold the key to understanding the very fabric of reality. Some of these phenomena are so strange, even scientists struggle to explain them. Others hint at forces and dimensions we've yet to discover, so buckle up. By the time we're done, you'll never look at the night sky the same way again. The universe is far weirder, far more violent, and far more magnificent than we ever imagined, and it's time to see why. One of the most jaw-dropping displays of power in the universe comes from quasars firing ultra-high-energy jets across unimaginable distances. These aren't just gentle streams of particles. They're violent, focused beams of plasma screaming through space at nearly the speed of light, stretching farther than entire galaxies. Picture a cosmic fire hose blasting matter millions of light years into the void, carving through space like a scalpel through fabric. But what's truly baffling is how these jets form in the first place. At the core of every quasar, a supermassive black hole feasts on swirling gas and dust, creating a maelstrom of energy so intense it rips apart atoms and flings them outward with unimaginable force. Scientists believe magnetic fields play a key role, twisting and channeling this chaos into focused beams. Yet even that explanation feels almost too neat. These jets move so fast they shouldn't stay perfectly straight over such vast distances. Some defy expectations by bending sharply as if guided by invisible hands, and their composition, a scorching soup of electrons, protons, and other charged particles, superheated to millions of degrees. When these jets slam into surrounding gas clouds, they trigger shockwaves capable of birthing new stars or sterilizing entire regions of space, preventing galaxies from forming at all. The sheer scale of destruction is matched only by their beauty. Some of these jets glow fiercely in radio waves, illuminating the cosmos like neon signs in the void. Others remain nearly invisible, detectable only by the ripples they leave in their wake. And here's the wildest part: these jets might be the universe's ultimate recyclers. By flinging material far beyond their host galaxies, they could be seeding the cosmos with the raw ingredients for future stars, planets, and even life. So while quasars might seem like cosmic monsters, they're also architects, shaping the universe in ways we're only beginning to understand. But sometimes nature plays tricks on us, tricks so convincing they seem to rewrite the laws of physics themselves. Take the case of quasar jets appearing to move faster than light. Yes, you heard that right, faster than light. At first glance, time-lapse observations reveal these jets blasting outward at speeds that should be impossible, violating Einstein's cosmic speed limit. But here's the twist: it's all an illusion, a cosmic sleight of hand known as superluminal motion. What's really happening is a mind-bending combination of relativity and perspective. Imagine a jet of material hurtling toward us at nearly light speed, angled just slightly in our direction. Because the jet is racing so close to the speed of light, the light emitted from later parts of the jet has less distance to travel to reach us than the light from earlier parts. The result, our brains, and even our telescopes get fooled into thinking the jet is moving faster than it actually is. It's like watching a cosmic version of a sonic boom, where the geometry of motion distorts our perception. This effect isn't just a curiosity, it's proof of how warped spacetime becomes under extreme conditions. The same relativistic effects that cause this illusion also mean time itself flows differently near these jets. For an observer riding along with the jet, everything would seem normal, but from our distant vantage point, the universe itself contorts to create this breathtaking illusion. And the implications go deeper. The fact that we see this at all tells us these jets aren't just fast, they're aligned almost perfectly with our line of sight, like staring down the barrel of a cosmic cannon. Miss that alignment by even a few degrees and the illusion vanishes. That's why only some quasars display this bizarre behavior, making it a rare and mesmerizing glimpse into the extreme physics governing the universe's most energetic phenomena. So while nothing actually breaks the speed of light, the very fact that nature can conjure such convincing illusions reminds us, when it comes to quasars, reality is often stranger than fiction. Now imagine finding two quasars separated by billions of light years, yet their light signatures match so perfectly. It's as if the universe photocopied them. These aren't just similar, their spectra align down to the most minute details, like cosmic twins sharing the same atomic fingerprint. At first glance, the odds seem impossible. After all, quasars are chaotic beasts, each with unique swirling disks of superheated gas and wildly varying conditions around their central black holes. So how could two exhibit such eerie symmetry? One leading theory points to gravitational lensing, where a massive object, like a galaxy cluster, bends and splits the light from a single distant quasar, creating multiple images that appear as separate quasars. It's nature's version of a funhouse mirror, warping spacetime to replay the same cosmic broadcast from slightly different angles. But here's the catch: in some of these cases, no lensing galaxy has been detected, leaving scientists scratching their heads. That's where things get even stranger. Some researchers have floated a far more radical idea: quantum entanglement on a cosmic scale. Could particles in these quasars somehow remain linked across vast distances, synchronizing their behavior instantaneously? It's a tantalizing thought, but the physics defies our current understanding. Entanglement typically operates on microscopic scales, not across galactic voids. Yet the precision of these spectral matches keeps the door open to wild possibilities, hinting at undiscovered forces or dimensions weaving the universe together in ways we can't yet comprehend. Then there's the third option: sheer, unfathomable coincidence. Quasars might have common building blocks, certain gases, temperatures, or magnetic fields that occasionally produce nearly identical light patterns purely by chance. Think of it like two unrelated orchestras separated by continents, somehow playing the same symphony note for note. Improbable, absolutely, but in a universe this vast, even the impossible might happen now and then. What makes these twin quasars so compelling isn't just the mystery, it's what they reveal about our place in the cosmos. Every time we think we've pinned down the rules, the universe throws a curveball, reminding us that reality's playbook is far stranger than we imagined. Whether it's lensing, quantum weirdness, or cosmic déjà vu, these spectral doppelgangers challenge us to rethink not just quasars, but the very fabric of existence itself. Just when we think we understand quasars, they pull another disappearing act, vanishing without warning, as if someone flipped a cosmic switch. These aren't gradual fades or slow dimming events. One moment, a quasar shines brighter than 1,000 galaxies. The next, it's gone, leaving astronomers staring at empty patches of sky where a powerhouse once roared. The most puzzling cases happen over mere years or even months, a blink of an eye in cosmic time. What could possibly shut down such an unfathomable energy source so abruptly? The leading suspect lies in the feeding habits of supermassive black holes. Think of a quasar as a black hole's dinner party. When it has a steady supply of gas and stars to devour, the surrounding disk heats up, glowing fiercely. But if the buffet runs dry, the light show stops. Some theories suggest giant molecular clouds or entire stars might collapse into the disk all at once, creating a temporary feast followed by sudden starvation. Other models propose that magnetic fields around the black hole could violently reorganize, choking off the flow of matter like a twisted hose shutting off water. Then there's the more dramatic possibility, a cataclysmic event. Picture two supermassive black holes locked in a gravitational dance during a galaxy merger. Their chaotic interaction could fling vast amounts of gas outward, robbing the system of fuel in one violent swoop. Alternatively, the black hole might have simply cleaned out its neighborhood, like a cosmic vacuum cleaner that's run out of dirt to suck up. But the implications go far beyond these vanishing acts. If quasars can switch off this quickly, it challenges our assumptions about how black holes grow and evolve. We've long thought of them as slow, steady accumulators, but what if they're more like unpredictable gourmets, binging and fasting in extreme cycles? This could rewrite our understanding of galaxy formation, as quasars play a crucial role in shaping their surroundings. A sudden shutdown might leave a galaxy's gas reserves frozen in place, halting star birth in its tracks. Even stranger, some quasars seem to flicker back on after millennia of silence, as if something reignited the furnace. That raises an even wilder question. Are these black holes just napping, not dead? The universe loves a good mystery, and these vanishing quasars are one of its most tantalizing. They remind us that even the mightiest forces in existence can be fleeting. Here one moment, gone the next, leaving us to piece together the clues they leave behind. In the vast cosmic ledger, redshift is supposed to be the universe's way of keeping score, a reliable measure of how fast distant objects are moving away from us, and by extension, how far they are in space and time. But quasars, true to their nature, love to break the rules. Some of these brilliant objects exhibit redshifts that don't align with their host galaxies, throwing a wrench into our most fundamental cosmological models. It's like finding a clock that ticks backward while hanging on a perfectly normal wall. How can an object embedded in a galaxy have a radically different redshift, implying it's either much farther away or hurtling through space at a wildly different velocity? This mystery isn't just a minor discrepancy, it sparked one of astronomy's most heated debates, led by the controversial astronomer Holton Arp. His observations suggested that quasars might not be the distant, ancient objects we assume, but instead could be much closer, ejected from active galaxies like cosmic sparks. Imagine a galaxy firing off quasars like bullets from a gun, their redshifts not reflecting distance but some unknown physical process. Mainstream astronomy dismissed Arp's ideas, clinging to the standard redshift-distance relationship. Yet decades later, oddball quasars continue to pop up, defying easy explanation. One possibility is that we're seeing light warped by unseen forces. Could gravitational lensing or exotic physics be distorting the redshifts, tricking our instruments? Or might quasars somehow inherit unusual velocities from their turbulent birth around supermassive black holes, like debris flung from a cosmic tornado? There's even the fringe hypothesis that redshift isn't purely about motion, that some intrinsic property of quasars or unknown physics could be at play. But the implications cut to the heart of cosmology itself. If redshifts can't always be trusted, how do we map the universe's expansion? Do we need to rewrite the textbook on cosmic distances? Every anomalous quasar is a flare in the dark, forcing us to question whether we've misunderstood the cosmos on the grandest scale. And that's the beauty of these outliers. They don't just defy expectations. They dare us to imagine a universe far more complex and far more mysterious than we ever thought possible. Galactic collisions are nature's ultimate fireworks show, cataclysmic events where entire galaxies crash together in a slow-motion ballet of destruction and rebirth. But these cosmic pile-ups aren't just about stars scattering like glitter in the wind. They're also the hidden catalysts behind some of the universe's most luminous phenomena, quasars. When two galaxies spiral toward each other, their gravitational dance doesn't just reshape their structures, it funnels vast reservoirs of gas straight into the supermassive black holes lurking at their cores. Like throwing gasoline on a fire, these violent inflows ignite quasars, transforming dormant black holes into ravenous beasts capable of outshining 1 trillion stars. Hubble's telescope has captured these cosmic demolition derbies in breathtaking detail. One iconic image shows the uncanny galaxies, their long, glowing tails of stars and gas stretched across space like celestial brushstrokes. Deep within this chaos, newborn quasars flicker to life as clouds of gas, wrenched loose by tidal forces, spiral toward the central black holes at speeds nearing 500,000 miles per hour. Simulations reveal the sheer violence of this process. Gas clouds collide, heat up, and shed angular momentum in a frenzied rush toward the center, triggering bursts of radiation so intense they can be seen clear across the observable universe. What's even more astonishing is the timing. Quasar activity often peaks after the merger's initial impact, as if the black hole needs time to digest its sudden feast. For millions of years, the supermassive black hole gorges on this buffet of gas, its accretion disk glowing white-hot under the strain. The resulting quasar becomes a beacon, illuminating the galaxy's turbulent core and even pushing back against star formation with its blistering winds, a cosmic case of the dinner guest rearranging the entire house. But here's the twist: not all mergers create quasars. The outcome hinges on the galaxy's gas reserves. Two gas-rich spirals colliding, that's prime quasar fuel. A merger dominated by older, gas-poor elliptical galaxies, the black hole might barely get a snack. This delicate balance explains why some cosmic smash-ups light up the universe while others fade into obscurity. And the implications are staggering. If galactic collisions are quasar midwives, then these events aren't just destructive. They're creative forces shaping the evolution of galaxies by regulating black hole growth and star formation. They might even explain why quasars were more common in the early universe, when galaxies were packed tighter and collisions were frequent. Every time we spot a quasar blazing in the depths of space, there's a good chance we're witnessing the aftermath of a cosmic car crash, one that set the stage for a new chapter in galactic history. At the edge of our cosmic maps, astronomers have stumbled upon quasars that shouldn't exist, objects so ancient. Their light appears to have traveled longer than the universe itself has been around. These impossible quasars, like J03131806 shining from a staggering 13 billion years ago, pose a breathtaking paradox. If the Big Bang occurred roughly 13.8 billion years ago, how can we see quasars that seem to have formed in less than 700 million years? That's like finding a fully grown tree in a forest that sprouted before the soil existed. The implications send shockwaves through cosmology, forcing us to question everything from measurement errors to the fundamental laws of physics. The most straightforward explanation points to timing quirks in our observations. Measuring cosmic distances isn't as simple as reading a clock. It relies on redshift, the stretching of light as the universe expands. But redshift interpretations can get messy near the dawn of time. where gravitational effects from the early universe's density might skew our calculations. Imagine trying to gauge the speed of a car through fogged-up glasses. Sometimes the tools we trust introduce blind spots. Some researchers argue that these quasars might simply be closer than their redshift suggests, their light warped by intervening galaxies or invisible dark matter structures we haven't yet mapped. Yet there's a more radical camp daring to ask, what if the constants governing physics weren't always constant? The fine structure constant, which dictates electromagnetism's strength, might have fluctuated in the early cosmos. Even a tiny variation could alter how atoms emitted light, making ancient quasars appear older than they truly are. It's like discovering an hourglass where the sand sometimes flows sideways suddenly. Timekeeping isn't so reliable. This idea, though controversial, gains traction from subtle anomalies in quasar spectra that hint at shifting physical laws. Then there's the elephant in the room. Could our cosmic timeline itself be incomplete? Alternate models like conformal cyclic cosmology suggest the Big Bang wasn't the absolute beginning but one phase in an endless cycle of universes. In this view, quasars might carry echoes of a prior cosmic epoch, their light bridging gaps our math can't yet fathom. While mainstream science remains skeptical, these outliers keep the debate alive, proving that the universe's earliest chapters might still hold surprises. What makes these ancient quasars so electrifying isn't just their defiance of textbooks, it's their power to expose the limits of human knowledge. Every time we think we've pieced together cosmic history, the universe tosses another puzzle our way, whispering that the story might be far stranger than we dreamed. Whether it's flawed measurements, evolving constants, or glimpses of a pre-Big Bang world, one thing's certain: the deeper we look, the less we seem to know. Staring into the abyss of deep space, astronomers sometimes catch a surreal sight, a blazing quasar, shining with the ferocity of a trillion suns, yet seemingly adrift in absolute nothingness. No swirling galaxy embraces it, no cluster of stars keeps it company, just a solitary beacon of light suspended in the void like a single lantern in an endless cave. These naked quasars defy logic. After all, every supermassive black hole should sit at the heart of a galaxy, right? So where are their hosts? One explanation cuts to the core of cosmic violence. These quasars might be survivors of galactic collisions ejected from their homes like cannonballs fired by gravitational slingshots. Picture two galaxies merging, their central black holes locked in a deadly dance. As they spiral closer, physics kicks in. A third object, whether a star, gas cloud, or another black hole, can steal some of the system's energy, flinging one of the black holes outward at incredible speeds. The result, a rogue quasar cast adrift into intergalactic space, its former galaxy left reeling from the cosmic upheaval. Hubble has spotted a handful of these runaway quasars, their high velocities betraying their violent past. But there's another, more elusive possibility. What if the galaxies are there, just too faint to see? Quasars are so blindingly bright, they can drown out the glow of entire galaxies. It's like trying to spot a candle next to a searchlight from across a continent. Advanced telescopes have peeled back the glare in some cases, revealing wispy, stretched-out galaxies stretched thin by gravitational interactions. These ghostly hosts, barely clinging to existence, suggest some quasars might have devoured or blown away their surroundings, leaving behind little more than a radiant core. Then come the true anomalies, quasars floating in regions so empty, not even the faintest galaxy lingers nearby. These might be relics from an era when the universe was smaller and denser, their original galaxies torn apart by ancient collisions we can no longer trace. Or perhaps they're feeding on dark matter filaments, invisible rivers of material snaking through the cosmos. Whatever the case, their isolation forces us to rethink how black holes grow and survive without a steady supply of galactic fuel. The mystery deepens when we consider time. In the early universe, galaxies were smaller and dimmer. Could some quasars have outshone their host so completely that today, billions of years later, we see only the quasar's afterglow, the galaxy itself faded into oblivion? It's a haunting thought that we might be witnessing the last embers of cosmic structures long since vanished, their brilliance preserved only by the stubborn light of their central black holes. Every missing host galaxy isn't just a puzzle, it's a window into the extremes of black hole behavior. Whether they're galactic fugitives, invisible dwarfs, or remnants of a bygone cosmic age, these lonely quasars remind us that the universe specializes in exceptions. For every rule we think we've etched in stone, there's a quasar drifting in the dark, waiting to rewrite it. Deep in the cosmic void, where galaxies appear as lonely specks in an ocean of darkness, quasars blaze like beacons not just for us but for the universe itself. Their unmatched brilliance does more than dazzle our telescopes. It pierces through the fog of intergalactic space, lighting up hidden structures we'd never see otherwise. Think of it as turning on a flashlight in a dusty attic. Suddenly, the invisible becomes visible. Among their most astonishing roles, revealing the cosmic web, the vast, delicate network of gas and dark matter that connects all galaxies in the universe like threads in a grand tapestry. When quasar light travels billions of light years to reach us, it doesn't arrive untouched. Along the way, it filters through clouds of hydrogen, helium, and other elements floating between galaxies. These clouds leave fingerprints, absorption lines etched into the quasar's spectrum like scratches on a lens. By decoding these lines, astronomers can map the otherwise invisible matter that weaves the cosmos together. It's as if quasars handed us a forensic kit, letting us reconstruct the universe's hidden architecture from shadows and echoes. Some of the most groundbreaking discoveries come from the Lyman Alpha Forest, a bizarre pattern of absorption lines caused by countless hydrogen clouds at different distances. Each line represents a strand in the cosmic web, a filament of gas threading through the void. Without quasars backlighting this faint gas, we'd be blind to these structures, like trying to study a spider's web in a pitch-black room. By analyzing these patterns, scientists have even found evidence for the missing baryon problem, locating vast reservoirs of ordinary matter that had eluded detection for decades. But quasars don't just expose the cosmic web structure, they illuminate its evolution. By studying light from quasars at varying distances and thus different cosmic eras, we can watch how the web changes over time. Early in the universe, the gas was denser and more chaotic, like a freshly spun spiderweb. Today, it's stretched thin by expansion, with matter concentrated in nodes where galaxies cluster. The real magic happens when multiple quasars line up behind the same gas cloud. Like overlapping spotlights on a stage, their combined light creates a 3D map of the intervening matter, revealing its texture, motion, and even temperature. Some quasars have unveiled gargantuan gas halos around galaxies, while others expose the shockwaves from ancient galactic collisions, frozen in the intergalactic medium like fossils in amber. Yet for all their illuminating power, quasars also deepen the mystery of the cosmic web. Some absorption lines hint at structures far larger than our models predict, filaments stretching hundreds of millions of light years, defying expectations of how matter should clump. Others show gas moving at inexplicable speeds, as if tugged by unseen forces. Every new quasar studied adds another piece to the puzzle, proving that even as lighthouses, these cosmic behemoths don't just reveal answers, they ignite new questions. In the end, quasars gift us more than light. They offer a way to see the invisible scaffolding of the universe, the hidden currents that shape everything from galaxy formation to the fate of cosmic expansion. Without them, the cosmic web would remain a ghost, felt but never seen. With them, we don't just observe the universe, we trace its bones. Light doesn't always travel through the universe in a straight line. Sometimes it dances. When it comes to quasars, that dance holds secrets. Astronomers have discovered that some of these cosmic powerhouses emit light with a strange property, polarization. Imagine light as a wave vibrating in every direction, like ripples spreading outward from a stone dropped in a pond. But polarized light, it's as if those ripples have been combed into perfect parallel lines, vibrating in just one plane. This twisting of light doesn't happen randomly. It's the signature of something invisible yet powerful at work: magnetic fields. Quasars are already chaotic environments, with superheated gas swirling around black holes at nearly light speed. But add magnetic fields into the mix and things get even wilder. These fields act like cosmic sculptors, channeling and shaping the quasar's jets, those narrow beams of plasma screaming across space. Polarized light reveals the hidden architecture of these magnetic fields, showing scientists how they spiral and twist around the jets, guiding their path like rails for a cosmic roller coaster. Without this polarization, we'd be blind to the forces that keep these jets focused over millions of light years instead of fanning out into chaos. Recent observations from the ALMA telescope have peeled back even more layers of the mystery. By studying polarized light from a quasar's jet in unprecedented detail, ALMA uncovered something shocking. The magnetic fields aren't just strong, they're organized in intricate spirals like the grooves on a vinyl record. This structure suggests the fields are generated by the violent rotation of the black hole's accretion disk, then amplified as they're wound tighter and tighter by the disk's spin. It's a cosmic dynamo, converting motion into magnetic energy on an unimaginable scale. Here's where it gets even more fascinating. These magnetic spirals might solve a long-standing puzzle: how quasar jets stay so stable over mind-boggling distances. Normally, plasma jets should disperse or wobble as they travel, like a garden hose flailing out of control. But the twisted magnetic fields act like a stabilizing force, keeping the jet tightly collimated, almost like a laser beam. Some researchers compare it to wrapping rubber bands around a bundle of sticks. The tension holds everything together against the forces trying to tear it apart. Yet polarized light doesn't just illuminate the jets, it also traces the environment around them. Some quasars show polarization patterns that flicker over time, hinting at turbulent magnetic storms raging near the black hole. Others reveal orderly fields stretching far into intergalactic space, suggesting these magnetic tendrils might influence gas clouds and even neighboring galaxies. It's as if quasars don't just dominate their surroundings with light and radiation, they might be quietly magnetizing the cosmos on a grand scale. The implications stretch beyond quasars themselves. If magnetic fields play such a pivotal role in shaping these jets, they might also be key players in other high-energy phenomena, from pulsars to gamma-ray bursts. Understanding how they work in quasars could unlock secrets about how energy is transported across the universe. And with telescopes like ALMA now capable of mapping these fields in exquisite detail, we're not just observing quasars, we're decoding the invisible forces that govern some of the most violent and beautiful events in existence. So the next time you hear about a quasar's brilliance, remember, it's not just about the light we can see. It's about the hidden magnetic fingerprints woven into that light, telling a story of power, structure, and cosmic control. In a universe full of chaos, these fields are the unseen hands shaping the storm. Some quasars don't just blaze with light, they whisper with ghosts. Astronomers have caught these cosmic giants emitting something bizarre, faint, delayed glimmers that act like echoes of eruptions from centuries or even millennia ago. Picture shouting into a canyon and hearing your voice bounce back, except here, the shout is a cataclysmic flare from a supermassive black hole, and the echo is its light finally reaching us after ricocheting off interstellar dust clouds millions of light years away. Hubble's observations of Quasar IC 2497 revealed one of the most stunning examples: a delayed glow from a flare that initially lit up around 20,000 years ago, its light now reflecting off a swirling dust screen like a cosmic rerun. What makes these echoes so valuable is their forensic detail. Unlike the blinding glare of an active quasar, the reflected light is softer, diffused, allowing telescopes to dissect its spectrum without being overwhelmed. It's like studying a wildfire not by staring into the flames, but by analyzing the soot patterns left on nearby trees. These echoes reveal the composition of the dust clouds, their distance from the quasar, and even the nature of the original eruption, details the quasar's current state might have erased. In one case, echoes showed evidence of a forgotten outburst 100 times brighter than the quasar appears today, a tempest now faded into cosmic memory. The parallels to supernova light echoes are striking, but with a key twist. When a star explodes, its echo is often a brief, expanding shell of light, like ripples from a pebble tossed in a pond. Quasar echoes, though, can linger for millennia, their light bouncing between multiple dust layers at different distances. This creates a time-lapse effect, multiple snapshots of the quasar's past activity, each encoded in light that took slightly longer paths to reach us. It's as if the universe installed a surveillance system, recording a black hole's tantrums in ultra-slow motion. But the real magic lies in what these echoes imply about quasars' life cycles. Some show evidence of violent, erratic bursts, proof that these objects aren't just steady beacons, but prone to fits of cosmic fury. Others suggest long periods of dormancy, their echoes the only clue that they were ever active at all. By piecing together these flickers from the past, astronomers are essentially building a time machine, reconstructing quasars' histories one reflected photon at a time. The most tantalizing echoes, however, might still be hiding. Theorists predict that some quasars could have produced eruptions so ancient their light hasn't even finished its detour to reach us yet. Future telescopes might catch these ultra-slow whispers, revealing chapters from a time when the universe itself was in its infancy. Until then, every echo we do detect is a reminder. Even the loudest voices in the cosmos leave traces if you know where to listen. Most stars forge the elements of the universe in their cores: carbon, oxygen, iron, the building blocks of planets and life itself. But quasars, they're the universe's alchemists, capable of creating elements so rare and heavy they defy conventional stellar furnaces. Astronomers have spotted quasars with bizarre chemical signatures, spectral lines revealing traces of gold, platinum, even uranium elements that shouldn't form in such abundance under normal cosmic conditions. It's like finding a bakery that somehow produces diamonds instead of bread. The presence of these exotic elements points to something extraordinary happening in the chaos around supermassive black holes, where physics twists into uncharted territory. The mystery begins with nucleosynthesis, the process that creates new atomic nuclei. In ordinary stars, heavy elements form slowly, layer by layer, through fusion or supernova explosions. But quasars operate on a different scale entirely. Near the accretion disk's inner edge, temperatures soar to trillions of degrees, and densities reach levels that crush matter into surreal states. Here, protons and neutrons might reassemble under extreme conditions, forging gold and uranium through rapid neutron capture, a process called the R process, typically linked to colliding neutron stars. Yet quasars seem to achieve this alchemy solo, without needing a catastrophic stellar collision. One theory suggests that the black hole's immense gravity creates a particle accelerator environment, where jets and outflows slam stray atoms together with enough force to synthesize heavy elements on the spot. Picture a cosmic smelting furnace, where magnetic fields hurl atomic nuclei at each other like subatomic pinballs, fusing them into heavier and heavier forms. Another idea points to the accretion disk itself, its turbulent eddies acting as elemental crucibles, where matter cycles through extreme pressures over and over, gradually building up rare isotopes. But the real shocker came when researchers found quasars with uneven elemental distributions, patches of space near the jets absurdly rich in gold or platinum, like cosmic gold rushes frozen in time. This clumping defies expectations. Heavy elements should diffuse evenly if forged in a uniform process. Instead, it hints at localized, violent events, perhaps pockets of the disk undergoing runaway nuclear reactions, or even chunks of neutron star material ripped apart and vaporized by the black hole's tides. What makes these chemical anomalies so fascinating isn't just their existence, it's their implications. If quasars can mass-produce gold and uranium, they might be the hidden factories behind some of the universe's heaviest elements. That challenges the long-held belief that neutron star mergers are the sole source of our process elements. Maybe, just maybe, the gold in your jewelry owes its existence to a quasar's fury billions of years ago. Even more tantalizing, these signatures might be clues to the black hole's feeding history. A sudden spike in uranium could signal the digestion of a neutron star, while excess platinum might trace back to a devoured white dwarf. Each element becomes a forensic marker, revealing the black hole's past meals like cosmic archaeology. As telescopes grow sharper, these chemical fingerprints could rewrite our understanding of everything from galactic evolution to the origins of life's rarest ingredients. So the next time you look up at the night sky, remember, some of the universe's most precious treasures aren't just hidden in the darkness, they're being forged in the hearts of its most violent infernos. Quasars are supposed to follow the rules, or at least that's what astronomers thought. The standard model tells us these cosmic powerhouses should be surrounded by a thick, donut-shaped ring of dust and gas called a torus, shrouding the supermassive black hole at their core. This dusty veil is so fundamental to our understanding of active galaxies that it forms the backbone of AGN unification theory. The idea that all quasars are essentially the same type of object, just viewed from different angles. But then there are the rebels quasars caught red-handed without their dust. These naked quasars flaunt their brilliance unobscured, their central engines exposed like cosmic exhibitionists. And their existence throws a wrench into everything we thought we knew about how these monsters operate. Take Quasar PDS 456, for example. This hyper-luminous beast blazes with the energy of 20 trillion suns, yet it shows almost no signs of the telltale dust that should be there. Where's the torus? Did it evaporate? Was it never there to begin with? The leading theory suggests these oddballs might represent a brief, violent phase in a quasar's life. When the black hole's radiation grows so intense, it literally blows away its own dusty cocoon. Imagine a hurricane so powerful it strips a forest down to bare rock. That's the scale of force we're talking about. The radiation pressure from the accretion disk becomes so overwhelming, it vaporizes nearby dust grains or flings them outward into intergalactic space, leaving the black holes more starkly visible. But there's another, even wilder possibility. Some naked quasars might be caught in the act of galactic feasting, their dust toruses not destroyed but temporarily displaced. When a supermassive black hole devours a massive gas cloud or even an entire star, the influx of fresh material can trigger an eruption of energy so sudden, it clears out the surrounding dust like a shockwave. Over time, the torus might reform, making these naked phases rare and fleeting glimpses into the black hole's feeding frenzy. It's like catching a dragon mid-meal, its fiery breath scattering the treasure hoard around it. Then there's the curveball. What if some quasars never had dust to begin with? Could the environment around a black hole's birth determine whether it grows up with a dusty cloak or not? In low metallicity regions of the early universe, where heavy elements and thus dust were scarce, quasars might have formed naked from the start. This would make them living fossils, relics of a time when the cosmos hadn't yet built up enough stardust to shroud its brightest monsters. The implications ripple far beyond just cataloging cosmic oddities. If naked quasars defy unification, then our entire framework for classifying active galaxies might need revision. Are they a distinct breed or just quasars caught in an extreme moment? Do they represent a youthful phase, an elderly one, or something else entirely? Every new naked quasar discovered forces us to reconsider the checklist of what makes a quasar a quasar. And in that uncertainty lies the thrill, because the universe's rule breakers are often the ones that teach us the most. So while textbooks might paint quasars as neatly dust-swaddled objects, the truth, as always, is far messier and far more fascinating. In the vast cosmic dance, not all quasars perform solo. Some whirl through space in pairs, locked in a gravitational embrace that defies imagination. These binary quasars aren't just rare cosmic curiosities. They're supermassive black holes, each weighing billions of suns, orbiting one another in a slow, inevitable spiral toward collision. Picture two bulls in a cosmic china shop, their immense gravity warping spacetime so severely they create ripples that could one day shake the entire universe. The discovery of these dueling titans opens a window into one of the most violent events nature can produce: the merger of supermassive black holes and the gravitational waves they'll unleash. Take the system as DSSJ 1536 plus 0441, where two quasars orbit just a few light-years apart, a hair's breadth in galactic terms. Their mutual pull distorts their accretion disks into chaotic, spiraling streamers, like two whirlpools sucking each other in. As they inch closer over millions of years, their orbital dance accelerates, reaching speeds that could circle Earth in seconds. The energy released isn't just light, it's raw spacetime distortion, vibrating the fabric of the cosmos itself. When these giants finally collide, the resulting explosion won't just be blinding, it'll send gravitational shockwaves across billions of light-years, detectable even here on Earth. This isn't just theoretical. LIGO, the Gravitational Wave Observatory, has already caught whispers of smaller black hole mergers, but binary quasars promise something far grander: low-frequency gravitational waves, rhythmic as a heartbeat, signaling the final moments before a merger. These waves could reveal secrets about black hole spin, the nature of spacetime, and even the fate of galaxies. After all, when two supermassive black holes unite, the recoil might kick the newborn monster clear out of its galaxy, leaving behind a wandering void in the cosmic dark. Yet the most tantalizing question remains: how do these pairs form in the first place? One leading theory points to galactic collisions. When two galaxies merge, their central black holes sink toward the new core through a process called dynamical friction, eventually forming a binary. But there's a catch: black holes should stall about a parsec apart, trapped in what's known as the final parsec problem. To merge, they need a third object, gas clouds, stars, or even a third black hole, to steal energy and push them closer. Some quasars, like OJ 287, showcase this drama in real time, with flares erupting every 12 years as the smaller black hole plunges through its partner's disk, heating gas to white-hot fury. Detecting these mergers won't be easy. Unlike stellar black holes, supermassive pairs take millennia to coalesce, their gravitational waves too low-pitched for current instruments. But upcoming telescopes like LISA, a space-based observatory, could tune into these cosmic bass notes, revealing a universe thrumming with the echoes of colliding giants. Every binary quasar we find is a preview of our Milky Way's fate billions of years from now. When Andromeda crashes into us, its black hole and ours will begin the same deadly dance. What's astonishing isn't just the scale of these events, it's their duality. Binary quasars are both destroyers and creators. Their collisions might sterilize entire galaxies, yet they also seed the cosmos with heavier elements and sculpt galactic structures. They're proof that even the universe's most violent acts are part of a cycle, one where endings spark new beginnings and where gravity, the quietest force, writes the loudest stories. The universe holds objects so luminous they redefine our understanding of brightness. Among them, quasars reign supreme, cosmic beacons capable of outshining not just stars but entire galaxies. Imagine a single point of light, no larger than our solar system, blazing with the intensity of 1 trillion suns. That's the staggering reality of quasar luminosity. To put this in perspective, our Milky Way, home to hundreds of billions of stars, radiates only about 1% of the energy produced by the brightest quasars. How can something so compact unleash such mind-bending brilliance? At the heart of every quasar lies a supermassive black hole, but it's not the black hole itself that shines. Instead, the light comes from the maelstrom of matter spiraling into it, an accretion disk of gas and dust heated to millions of degrees. As this material swirls inward, friction and magnetic forces churn it into a white-hot frenzy, converting mass into energy with terrifying efficiency. While the Sun transforms only about 0.7% of its nuclear fuel into light via fusion, a quasar's accretion disk can achieve efficiencies exceeding 10%. That's like comparing a campfire to a thermonuclear explosion, but raw efficiency isn't the only factor. The sheer volume of fuel matters too. Some quasars guzzle down entire suns' worth of gas every year, a feeding frenzy that borders on the incomprehensible. Picture a cosmic whirlpool where stars, gas clouds, and even planets are shredded into plasma, their energy released in a blinding flash before vanishing beyond the event horizon. This relentless consumption sustains luminosities that can temporarily eclipse every star in their host galaxy combined. What's truly humbling is the scale of time and space over which these monsters operate. The brightest quasars, like SDSS 08096+4821, shine from over 12 billion light-years away, meaning their light began its journey when the universe was barely a billion years old. Yet even across that unfathomable gulf, their brilliance pierces the darkness with ease, illuminating the universe's infancy like cosmic flashbulbs. These aren't just objects, they're time capsules, preserving a violent era when galaxies and black holes grew hand in hand through chaos and fire. Yet for all their ferocity, quasars also teach us about cosmic balance. Their luminosity isn't infinite, it's constrained by physics in surprising ways. There's a theoretical upper limit known as the Eddington limit, where radiation pressure from the quasar's own light pushes back against infalling matter, preventing it from eating too fast. Some quasars flirt with this boundary, their light so intense it nearly starves the black hole that fuels them. Others, however, seem to exceed it, suggesting even our best models might be missing pieces of the puzzle. This dance of creation and destruction shapes the universe itself. Quasars don't just burn, they sculpt, their radiation carving bubbles in intergalactic gas and regulating star formation across entire clusters. Their light seeds the cosmos with energy, while their eventual dimming leaves behind galaxies forever changed. So when we gaze at a quasar's brilliance, we're witnessing more than raw power. We're seeing the universe's heartbeat, a rhythm of growth, destruction, and rebirth written in photons older than Earth itself. Hidden in the depths of space, certain quasars act like cosmic time capsules, their light carrying the pristine chemical fingerprints of the universe's infancy. These rare objects harbor clouds of gas so untouched by stellar pollution, they offer a direct window into the primordial soup that existed before the first stars ignited. Unlike most of the cosmos, where generations of supernova have seeded space with heavy elements, these quasars float in bubbles of almost pure hydrogen and helium, conditions unchanged for over 13 billion years. Studying them is like finding an ancient vial of air from Earth's earliest atmosphere, except this air dates back to the cosmic dawn itself. One standout example is Quasar J 1342+0928, its spectrum revealing gas with metal levels 10,000 times lower than our Sun's. That absence speaks volumes. Heavy elements like carbon or oxygen common in today's universe form inside stars and spread through explosions. But this quasar's gas predates even the first stellar furnaces, preserving the universe's original chemistry like a fossil trapped in amber. The discovery sent shockwaves through astrophysics, proving pockets of the early universe survived unscathed, sheltered from the pollution of star birth and death. But these relics do more than satisfy curiosity. They're reshaping our understanding of cosmic reionization, the universe's pivotal transition from darkness to light. After the Big Bang, space was filled with a fog of neutral hydrogen, blocking ultraviolet radiation. Then, something ionized that gas, clearing the fog and allowing light to travel freely. Quasars were once prime suspects, their radiation thought powerful enough to strip electrons from hydrogen atoms. Yet pristine gas quasars complicate that story. Their untouched surroundings suggest some regions avoided reionization entirely, or that the process was patchier than models predicted. The implications ripple outward. If reionization wasn't uniform, it means the first stars and galaxies didn't light up the universe like a grid of street lamps. They flickered to life unevenly, leaving behind islands of darkness. These quasars might mark the borders of those islands, their pristine gas acting like cosmic tide pools, preserving conditions from an era when the universe was still figuring itself out. Future telescopes like the James Webb could use them as guideposts, mapping the shadows and spotlights of the early cosmos in unprecedented detail. What's most astonishing isn't just their purity, it's their resilience. Against all odds, these gas clouds endured eons of galactic collisions, quasar outbursts, and the slow churn of cosmic expansion. They're silent witnesses to the universe's entire history, holding secrets older than time itself. And with every new pristine quasar discovered, we get closer to answering the ultimate question. How did a featureless sea of gas become the glittering cosmos we know today? The answer might not lie in the brightest quasars, but in the faint, untouched whispers of the past they've somehow kept alive. Even the most violent cosmic monsters can sometimes flicker, like a candle caught in the wind. Some quasars emit X-rays with bizarre, unpredictable dips and flares, their high-energy signals wobbling as if something unseen were passing in front of them. These aren't just minor fluctuations. We're talking about X-ray emissions plunging by half or even vanishing entirely for days, only to roar back without warning. It's as if a cosmic hand keeps twisting the dimmer switch on a spotlight, leaving scientists scrambling for an explanation. One leading theory points to the accretion disk itself, not as a smooth, glowing pancake of gas, but a turbulent, clumpy mess. Imagine a whirlpool filled with icebergs. As these dense lumps of cooler gas orbit the black hole, they might momentarily block our view of the hottest X-ray emitting regions near the event horizon. These shadows wouldn't just dim the light, they'd warp its spectrum, imprinting telltale signatures on the X-rays that reach us. Some quasars, like MCG-630015, show this exact behavior, their X-rays flickering like a faulty neon sign. But there's a twist. Not all dips are created equal. Some quasars exhibit X-ray flares so abrupt and intense, they defy the clumpy disk explanation. Here, astronomers suspect hidden actors, stellar corpses like neutron stars or even smaller black holes, orbiting the supermassive beast. Picture a cosmic David and Goliath, a neutron star barely 20 kilometers wide, skimming the accretion disk's edge. Every close pass could trigger a titanic splash, heating gas to X-ray brilliance before the star's gravity rips the flare away. Others propose more exotic culprits, like runaway magnetic reconnection events. Think solar flares, but scaled up to galactic proportions. Then there's the real enigma, quasars whose X-rays vanish entirely for years, then reignite without explanation. These aren't mere flickers, they're full blackouts, as if a curtain drops over the black hole's maw. One radical idea suggests the inner disk might periodically collapse into the black hole, starving the X-ray region until fresh gas spirals in to rebuild it. It's like watching a volcano repeatedly bury its own vent, only for pressure to blast it open again. What makes these X-ray mysteries so tantalizing isn't just their strangeness, it's what they reveal about black hole diets. If clumps or companions trigger these signals, they're proof that feeding supermassive black holes isn't a smooth process. It's chaotic, messy, and full of surprises, like trying to study a hurricane by the debris it flings outward. Every anomalous flicker is a clue hinting at forces and structures we can't yet see. And with next-generation X-ray telescopes set to launch, we might finally decode the universe's most erratic light show. Every cosmic engine has its limits, or at least that's what physicists once believed. The Eddington limit, a fundamental rule of astrophysics, states that a black hole can only shine so brightly before the pressure of its own radiation pushes away the very gas feeding it. It's like a fire so hot it blows out its own oxygen supply. Yet some quasars laugh in the face of this law, blazing with intensities that should be impossible. Their brilliance isn't just extraordinary, it's outright defiant, forcing scientists to ask, are we missing something fundamental about how the universe works? Take the quasar SMSSJ0215 plus 1355, for example. This monster pumps out energy at more than 10 times its predicted Eddington limit, as if physics itself took a coffee break. Normally, radiation pressure should cap a black hole's growth, preventing it from devouring matter too quickly. But here, the rules seem rewritten. One explanation: these overachievers might be dining on an all-you-can-eat buffet of gas, swallowing it so fast that the radiation can't keep up with blowing it away. Picture trying to extinguish a bonfire with a garden hose while someone pours gasoline the flames win. But there's a catch. Such reckless feasting should tear apart the delicate balance of the accretion disk, creating chaotic, unstable conditions. Yet these quasars shine steadily, their light curves smooth as polished glass. That paradox has led to wilder theories, like hidden magnetic fields acting as cosmic bouncers, channeling gas into the black hole faster than radiation can protest. Others suggest the Eddington limit itself might need tweaking in extreme environments, where relativity warps the rules we take for granted. Then there's the measurement problem. Could we be fooled by geometry? If a quasar's jet points straight at us, its light gets artificially boosted, like a car's headlights blinding you on a dark road. But even after accounting for this beaming effect, some quasars still break the scale, and that's where things get truly intriguing. A handful of candidates, like the ultra-luminous quasar APM 08279 plus 5255, emit so much energy they might be tapping into entirely unknown processes, spinning black holes acting as cosmic dynamos, or even hints of exotic physics beyond Einstein's equations. What's at stake isn't just a record-breaking luminosity contest. If black holes can consistently surpass the Eddington limit, it reshapes our understanding of how they grow. The supermassive black holes we see in the early universe, already fully formed when the cosmos was young, might have gorged themselves in these extreme bursts. Their defiance could explain how they packed on billions of solar masses so quickly, like a bodybuilder gaining muscle overnight without stopping for rest. Yet for all their bravado, these rule-breaking quasars also humble us. They're reminders that the universe doesn't always play by the tidy rules we scribble in textbooks. Sometimes it throws a tantrum, smashing through ceilings we thought were unbreakable. And that's the real lesson here. When it comes to quasars, even the laws of physics might just be suggestions. Most cosmic objects flicker unpredictably, their brightness rising and falling like static on a screen. But some quasars pulse with eerie regularity, their light curves rising and falling in steady rhythms, like a heartbeat echoing across the cosmos. These clockwork quasars don't just vary randomly, they tick with precision, their brightness oscillating every few hundred or even thousand days with a stability that rivals atomic clocks. It's as if the universe itself set a metronome inside these monsters, marking time in a way that defies the chaotic violence at a black hole's edge. The most famous example, Quasar OJ287, has been monitored for over a century, and its 12-year cycle is so precise, astronomers have used it to test Einstein's theory of relativity. Each flare peaks within weeks of its predicted arrival, as reliable as a celestial train schedule. But unlike trains, this rhythm isn't mechanical. It's born from the delicate dance of two supermassive black holes locked in orbit. The smaller black hole plunges through the larger one's accretion disk like a spoon stirring molten lava, triggering bursts of light every time it heats the gas to white-hot fury. These aren't just flashes, they're cosmic sonar pings, revealing the black hole's masses and orbits with stunning accuracy. Yet single black holes can produce heartbeats too. In some quasars, the regularity points to a different phenomenon, resonances within the accretion disk itself. Picture a vinyl record warping as it spins, certain grooves vibrating more than others. In a quasar's disk, gravity and rotation create similar sweet spots, where matter piles up and releases energy in rhythmic bursts. Some models suggest magnetic loops snapping like rubber bands, while others propose spiral density waves sloshing through the disk like tides in a bathtub. The result is the same, a quasar that doesn't just shine but sings, its light pulsing in harmonies dictated by the black hole's gravity. What's even wilder is how these heartbeats can persist for decades, even centuries. Most cosmic processes are messy and short-lived, yet these oscillations endure, resisting the disk's turbulence like a lighthouse beam cutting through a hurricane. Some researchers speculate they're self-sustaining, the disk's own feedback loops keeping the rhythm alive, like a pendulum that never loses energy. Others think hidden forces, like undiscovered planets or stars orbiting near the black hole, might act as cosmic pacemakers, their gravity nudging the disk into sync. But the real magic lies in what these pulses reveal. Every beat is a probe into the black hole's hidden environment, exposing details no telescope could see directly. The timing hints at the disk's temperature and density. The amplitude unveils magnetic field strengths. Some heartbeats even show subtle drifts, their cycles speeding up or slowing down like a dying watch, clues that the black hole's feast might be nearing its end, or that a companion object is creeping closer. For astronomers, these rhythmic quasars are more than curiosities, they're tools. Like a doctor listening to a patient's pulse, they use these cosmic heartbeats to diagnose black holes, measuring their spin, mass, and even the warping of spacetime around them. And with new surveys monitoring millions of quasars, we're finding more of these timekeepers every year, each one adding another verse to the universe's grand symphony. So while black holes might seem like silent predators, some whisper in rhythms, steady, secret, and waiting to be heard. Light from distant quasars is more than just cosmic radiation. It's a message in a bottle cast across billions of years. When we observe these brilliant objects, we're not just seeing them as they are now, but as they were when their light first began its journey through the expanding universe. Each photon carries a snapshot of conditions from an era long before Earth existed, making quasars the ultimate time machines. Take Euler's J1342 plus 0928 for instance, a quasar so ancient, its light has traveled nearly 13 billion years to reach us. That means we're witnessing it as it appeared when the universe was a mere 700 million years old, a cosmic toddler still finding its footing. What makes these time capsules so revealing isn't just their age, it's the details etched into their light. As quasar radiation passes through intergalactic gas clouds, certain wavelengths get absorbed, leaving dark lines in their spectra like notches on a tree ring. These absorption lines act as chemical barcodes, recording the composition of the early universe. Some quasars, like J03131806, show spectra almost entirely devoid of heavy elements, proving they formed in a time before stars had polluted space with metals. Others reveal the fingerprints of the universe's first supermassive black holes, their light warped by gravitational lensing from invisible dark matter structures we can't detect any other way. But the real power of these cosmic relics lies in their ability to chronicle universal change. Compare the spectrum of a 13 billion-year-old quasar to one from only 10 billion years ago, and you'll see the gradual enrichment of space with carbon, oxygen, and iron, the building blocks of planets and life. Some quasars even capture the epoch of reionization, when the first starlight burned away the hydrogen fog filling the early cosmos. Their light bears the scars of that transition, with patches of neutral hydrogen absorbing specific ultraviolet wavelengths in patterns that map this pivotal era like a fossilized timeline. Perhaps most astonishing is how crisp these records remain despite their unimaginable journey. The light from quasar PSO J036+03, observed by the Gemini telescope, shows absorption features so sharp they could only have survived if the intervening space was far colder and less turbulent than models predicted. This forced astronomers to reconsider how structure formed in the early universe, revealing vast, quiet regions where gas remained undisturbed for eons. Every ancient quasar is both a witness and a puzzle. Their light confirms some theories while dismantling others, offering glimpses of a universe far stranger than our simulations suggested. And with next-generation telescopes like the LT set to probe even deeper, we're on the verge of decoding messages from the cosmic dawn itself, written in photons older than the atoms in our bones. Among the swirling chaos of a quasar's light, astronomers sometimes catch spectral lines that shouldn't be there, emission signatures defying the very rules that govern atomic physics. These forbidden lines aren't just rare, they're cosmic contradictions, glowing fingerprints of elements emitting light under conditions so extreme, nature's usual playbook gets tossed out the window. Normally, atoms follow strict quantum rules about when and how they can release energy. But in the maelstrom around a supermassive black hole, the unthinkable becomes routine, and these forbidden lines become screaming witnesses to forces beyond our everyday experience. Take the quasar 3C273, whose spectrum blazes with the forbidden emission of doubly ionized oxygen. In a lab on Earth, this line would vanish instantly. The excited oxygen atoms would collide with others before they could emit that specific wavelength. But in the thin, hyper-energized gas near a quasar's core, atoms have room to linger in improbable states, like acrobats suspended mid-flip without a net. The key lies in the environment, densities so low and radiation so intense that atoms behave unlike anything we can recreate. It's like finding ice in a furnace, a paradox that shouldn't survive, yet thrives against all odds. But forbidden lines don't just hint at unusual conditions, they map the invisible. Some quasars show these emissions Doppler shifted into bizarre patterns, revealing gas swirling at fractions of light speed. Others display forbidden lines split into multiple components, evidence of magnetic fields strong enough to twist atomic energy levels like pretzels. In extreme cases, like the quasar PKS 0405-123, the lines appear brighter than the models allow, suggesting processes we haven't even named yet. These anomalies force physicists back to the drawing board, questioning whether forbidden really means impossible or just we haven't seen the right extremes yet. The real shock comes when these lines flicker. In a handful of quasars, forbidden emissions vanish and reappear over months, as if someone were flipping a cosmic switch. Explanations range from clumps of gas evaporating under sudden radiation, bursts to entire regions of the accretion disk magnetically pinching off, altering the density in an instant. Picture a thunderstorm where raindrops periodically freeze in midair. That's the level of strangeness we're dealing with. Yet these rebellious spectral lines aren't just scientific nuisances, they're lifelines. By decoding them, astronomers measure black hole masses, map accretion disk structures, and even probe the elusive physics of plasma at the edge of annihilation. Every forbidden line is a flare in the dark, illuminating the wild frontiers where our laws of physics meet the universe's untamed reality. And that's the irony. What we call forbidden might just be nature's way of showing us how much we still have to learn. Quasars have long been branded as cosmic wrecking balls, their blistering radiation and supersonic jets capable of sterilizing entire galaxies by blowing away the gas needed for star formation. But the universe loves a good plot twist, and some of these violent powerhouses are turning out to be unlikely midwives for newborn stars. Take the so-called teacup quasar, officially known as SDSSJ 1430 plus 1339. At first glance, it fits the classic quasar mold, a supermassive black hole devouring matter at its core, launching jets that stretch tens of thousands of light years into space. But instead of the expected trail of destruction, astronomers found something astonishing: clusters of young stars lining the jet's path like cosmic breadcrumbs, sparkling proof that the quasar's fury had sparked creation, not just chaos. How does this happen? Picture a high-pressure fire hose blasting into a pile of dust. Normally, it would scatter everything, but if that dust is dense enough, the shockwave from the jet can actually compress pockets of gas, triggering gravitational collapse. In the teacup's case, its jets plowed into massive, cold molecular clouds, squeezing them until they reached critical density. Like a cosmic version of striking flint, the pressure ignited star formation along the jet's edges, stellar nurseries blooming in the unlikeliest of places. This phenomenon, dubbed positive feedback, flips the script on quasars, revealing their dual nature as both destroyers and creators. Other examples push the paradox further. The quasar He 2459 plus 0023, located 700 million light-years away, boasts jets so powerful they've carved bubbles in intergalactic space. Yet inside those bubbles, infrared telescopes spotted a surprise: scores of young, massive stars. The leading theory suggests the quasar's jets heated surrounding gas just enough to prevent it from cooling too quickly, allowing it to clump gradually into stars rather than being blown apart. It's a delicate balance, like a blacksmith tempering steel. Too much heat and the metal shatters, just enough and it takes shape. What's truly mind-bending is the scale of this star-forming influence. In some galaxy clusters, quasars have been caught seeding stars not just locally, but across distances spanning millions of light-years. Their jets act as cosmic conveyor belts, transporting energy and raw materials to far-flung gas clouds that would otherwise remain dormant. The implications rewrite galactic evolution. Quasars might not just regulate star formation in their host galaxies, but sculpt entire galactic neighborhoods, leaving behind legacies of light where we expected only devastation. This duality forces us to rethink the role of black holes in the cosmic order. Far from being mere engines of destruction, they emerge as key players in a cycle of renewal, scattering the seeds of new stars even as they consume the old. The teacup and its kin are reminders that in the universe's grand tapestry, violence and creation often share the same thread, and that some of the brightest beacons in the darkness might just be lighting the way for the next generation of stars. Some of the universe's most energetic displays don't just shoot straight, they twist, wobble, and spiral through space like celestial dancers. Among quasars, a rare few defy the usual straight arrow jets, instead launching plasma streams that corkscrew outward in hypnotic patterns. These dancing jets aren't just cosmic eye candy, they're clues to the chaotic environments around supermassive black holes where gravity and spin warp the very fabric of reality. Take Quasar 3C273, whose jet doesn't just pierce the void. It undulates like a ribbon in the wind, its path winding through space for thousands of light years. The leading explanation: a black hole spinning so fast, its axis wobbles like a top about to fall, dragging the jet along in a slow, cosmic pirouette. This phenomenon, known as precession, occurs when a black hole's spin axis doesn't align with its accretion disk, creating a lopsided tug-of-war that sends the jet spiraling outward. The physics mirrors a child's spinning top. Except here, the top weighs billions of suns, and its wobble reshapes entire galaxies. But precession isn't the only choreographer at work. Some quasars, like the enigmatic S50014813, showed jets that switch directions abruptly, as if yanked by invisible strings. Here, astronomers suspect hidden companions, smaller black holes or dense star clusters orbiting the central monster. Their gravitational nudges could torque the accretion disk, forcing the jet to pivot like a garden hose caught in a gust. In extreme cases, these companions might even plunge through the disk periodically, sending shockwaves that kink the jet's path like a finger bending a water stream. The most spectacular cases reveal helical jets, coiled like DNA strands stretching across interstellar space. These intricate spirals suggest more than just a wobbly black hole. They hint at magnetic fields winding tighter than a clock spring, channeling plasma into rotating columns. The Quasar 3C454.3 showcases this beautifully, its jet glowing in radio waves as it corkscrews away from the core. Simulations show these structures might emerge when the black hole's spin twists magnetic field lines into knots, turning the jet into a spinning drill bit of superheated plasma. What makes these dancing jets so valuable isn't just their spectacle, it's what they reveal about black hole dynamics. A precessing jet, for instance, lets astronomers measure a black hole's spin rate and tilt indirectly. A kinked jet might betray the presence of unseen companions, offering a new way to hunt binary supermassive black holes. Even the helix shape holds secrets. The tighter the spiral, the stronger the magnetic fields at play. Yet some patterns still baffle researchers. A handful of quasars exhibit jets that don't just wiggle. They serpentine, flipping direction every few thousand years like a cosmic switchback. These erratic paths might trace the orbits of multiple black holes in a chaotic dance, or reflect instabilities in the disk itself, where gas clumps disrupt the jet's flow like rocks diverting a river. The quasar PKS 2155-304 stands out here, its jet zigzagging so sharply, astronomers initially mistook it for separate objects. The implications stretch far beyond single quasars. If these jets can bend without breaking, it challenges assumptions about how structures remain stable under such extreme forces. Some models now suggest magnetic fields act like guide wires, keeping the jets coherent even as they flex. Others propose the plasma itself resists dispersion through internal turbulence, like a wildfire maintaining its shape despite shifting winds. Every dancing jet is a testament to the universe's flair for turning violence into art. What begins as a superheated beam of destruction becomes, across light years, a cosmic ballet, one where gravity, spin, and magnetism partner in a performance billions of years in the making. And for astronomers, each twist and turn is a step toward decoding the hidden rhythms of the cosmos. Quasars embody destruction on a cosmic scale. Their radiation and winds can sterilize galaxies, halting star formation for eons. But some of these blazing monsters lurk in galaxies already long dead, their stellar nurseries silent and dark. These ghostly hosts raise a chilling question. Did the quasar kill its galaxy, or did it awaken in a graveyard? The answer rewrites our understanding of how black holes and galaxies grow, or fail together. Take the quasar a DS17874555, sitting at the heart of a massive elliptical galaxy where no new stars have formed in billions of years. This isn't a galaxy in its prime, it's a cosmic fossil, its gas reserves exhausted or blown away. Yet the quasar still shines, a paradox that defies simple explanations. One leading theory suggests these quasars are living on borrowed time, their brilliance fueled by the last scraps of gas spiraling into the black hole, like a candle flaring brightly just before it gutters out. Without fresh fuel, the quasar's days are numbered, its light destined to fade as the black hole's meal dwindles to nothing. But there's a darker possibility. Some dead galaxies might not be dead at all. Their star formation could be suppressed, not extinct, with vast reservoirs of cold gas lurking just beyond the quasar's reach. Observations of the Phoenix cluster revealed exactly this, a galaxy classified as red and dead, yet hiding enough cold gas to birth billions of stars. The quasar's radiation might be keeping that gas too hot to collapse, like a lid clamped on a boiling pot. In this scenario, the galaxy isn't a corpse. It's a patient in suspended animation, its star-forming potential locked away until the quasar's grip weakens. The plot thickens when we consider timing. Some dead galaxies host quasars that flicker sporadically, as if the black hole is cycling between feasting and fasting. This fits a radical idea that supermassive black holes can choke on their own feedback. When a quasar's radiation blows away too much gas too quickly, it starves itself, only to reignite when residual matter drifts back centuries later. It's a self-limiting cycle, one that could leave galaxies in a perpetual state of near death, their star formation stuttering but never fully ceasing. Yet the strangest cases are the outliers, quasars in galaxies so ancient and depleted. Even the black hole's presence defies logic. How does a quasar stay active in a system where every visible gas cloud vanished eons ago? One clue comes from rogue planets and stellar remnants. Over billions of years, stars die, shedding layers or colliding, while icy bodies in the Oort cloud equivalents get nudged inward. These scraps might funnel just enough material toward the black hole to sustain a faint quasar, like a campfire fed by twigs after the logs have burned away. The implications stretch beyond individual galaxies. If quasars can persist in dead hosts, it suggests black holes are far more resourceful and galaxies more resilient than we imagined. A galaxy declared dead might just be biding its time, waiting for the quasar to sleep so it can breathe new stars into the void. Or perhaps some quasars are the last gasps of systems that sacrificed their future to feed a monstrous heart. Either way, these cosmic contradictions remind us that in the universe, death is rarely absolute, and sometimes it's just another kind of equilibrium. Quasars do more than blaze across the cosmos. They're celestial detectives, uncovering clues about the universe's most elusive substance, dark matter. This invisible material, which outweighs regular matter 5 to 1, refuses to interact with light, making it nearly impossible to observe directly. But quasars, with their piercing brilliance, offer a workaround. As their light travels through the cosmos, dark matter's gravitational grip bends and warps it, leaving subtle distortions that act like cosmic fingerprints. These distortions, known as weak gravitational lensing, don't just hint at dark matter's presence, they map its hidden architecture, revealing vast halos and filaments weaving through the void. The process starts with alignment. When a quasar's light passes near a massive galaxy cluster laden with dark matter, space-time itself curves, subtly twisting the quasar's image into faint arcs or smears. By analyzing thousands of these distorted quasars, astronomers have begun tracing the unseen scaffolding of the universe. One groundbreaking study used quasars behind the galaxy cluster Abell 1689 to reconstruct its dark matter distribution in 3 dimensions, like shining a flashlight through fog and tracing the shadows. The result, a ghostly blueprint of dark matter's tendrils, far more intricate than simulations predicted. What makes quasars uniquely suited for this hunt is their constancy. Unlike flickering stars or variable galaxies, quasars shine with unwavering intensity, their point-like images making distortions easier to isolate. The Sloan Digital Sky Survey has already harnessed this, using quasars to identify dark matter clumps so tiny they'd evaded detection for decades. Some of these micro-halos, weighing less than a dwarf galaxy, challenge theories about how dark matter should cluster at the smallest scales. It's like discovering invisible pebbles in a river we thought was smooth, proof that the cosmic dark matter web is far knottier than we imagined. The future promises even sharper insights. The Vera Rubin Observatory's Legacy Survey of Space and Time, or LSST, will scan the sky with unprecedented depth, capturing millions of lensed quasars. This avalanche of data could reveal dark matter's fine-scale structure, potentially exposing cracks in our current models. If dark matter is cold, as most theories suggest, its halo should be dense at the center. But if quasars show smoother distributions, it might hint at warm, dark matter particles just heavy enough to leave a different gravitational signature. Beyond mapping, quasars might expose dark matter's quirks. Some theories predict rare collisions between dark matter particles could produce gamma rays or other signals. Quasars located near these anomalies could become accidental dark matter laboratories, their environments magnifying faint emission we'd otherwise miss. Others speculate that certain spectral anomalies in quasar light, unexplained absorption lines or energy dips, could trace interactions between dark matter and ordinary particles, a ghostly handshake finally made visible. The grandest hope that quasars will help solve dark matter's ultimate riddle, what it's made of. If certain particles, like actions or WIMP, exist, their subtle effects on quasar light polarization or timing could betray their presence. It's a cosmic game of hide and seek where quasars hold the flashlight. With every new lensed image, every anomalous flicker, we're not just studying dark matter's shadow. We're decoding the invisible threads that bind the universe together. And in that decoding, we might finally answer one of science's oldest questions. What is the cosmos truly made of, from the jets racing faster than light, or at least appearing to the ghostly echoes of eruptions long past? Quasars and active galactic nuclei have proven themselves as the universe's most dazzling rule breakers. We've seen them vanish overnight, flicker with uncanny precision, and even forge elements too heavy for stars to create. They've shown us magnetic fields strong enough to sculpt plasma into spirals, and dark matter halos invisible to every tool but their lensed light. Some blast galaxies with radiation fierce enough to halt star birth, while others spark it along their jet-streamed paths like cosmic gardeners. They've defied the Eddington limit, rewritten the rules of redshift, and left us questioning whether we've even glimpsed the full scope of their power. Each of these 25 phenomena isn't just a cosmic oddity, it's a crack in the door of our understanding, inviting us to pry it open wider. When quasars flicker, they expose the turbulence of black hole feasts. When their jets dance, they trace the warping of spacetime itself. Even their forbidden spectral lines are cryptic postcards from the edge of physics, where the universe laughs at our lab-tested rules. And let's not forget the ancient ones, those time capsules whose light predates Earth, carrying whispers from an era when the cosmos was raw and untamed. But here's the real magic. Every quasar mystery solved spawns 3 new questions. Those twin quasars with matching spectra, they challenge how we measure distance. The naked quasars missing their dust, they append decades of unification theory. Even the heartbeat rhythms of clockwork quasars force us to rethink how black holes spin, feed, and interact with their surroundings. That's the gift of these cosmic enigmas. They don't just push boundaries, they redraw the map entirely. So as we wrap up this journey through the universe's most bewildering powerhouses, we're left with one burning question: which phenomenon rocked your world the most? Was it the quasars shaping galaxies instead of destroying them, the ones rewriting the periodic table in their accretion disks, or maybe the rogue quasars drifting through the void, unshackled from their galactic homes? Drop your favorite in the comments, because the wildest part isn't just what we've discovered, it's what's still out there waiting to be